See how far you've brought me, Lord, have come to worship you. See how far you've brought me, Lord, I've come to worship. Say, see how far, see how far you brought me. Lord, I've come, Lord, I've come to worship. Say, see how far.
Distinguished ladies and gentlemen, good afternoon. The student, can you please move forward, please? Can you move forward? Can we be upstanding for the university procession? Let's remain standing for the university anthem. University of Lagos, the rising sun, our fountain of excellence, our citadel of learning, my God, our God, for all sound minds. We rise beyond the
seated. The Deputy Vice Chancellor, Development Services, Professor Afolabi Leshi. The Deputy Vice Chancellor, Management Services, Professor Muyiwa Falaye. The Deputy Vice Chancellor, Academics and Research, Professor Matthew Ilori. The Registrar and Secretary to Council, Mrs. Victoria Abosede Wycliffe. The Bursar, Mrs. Oluwafumilola Adekunle. The University Librarian, Professor Christopher Okiki, ably represented by Professor Adetoun Adekonye. The Provost College of Medicine, Professor Ademola Oremosu. The Dean, Faculty of Engineering, Professor Samson Adeoshun, ably represented by Professor Folorunsho Ogunwolu. Distinguished ladies and gentlemen, gentlemen of the press, it is with immense pleasure that I welcome you to the 459th Inaugural Lecture of the University of Lagos. Today's lecture, the 13th in the 2025-2026 academic session, will be delivered by Professor Faith Uchenna Babalola of our Department of Chemical Engineering, Faculty of Engineering. Born on the 22nd of January 1966 in Nnewi, Anambra State, Professor Babalola obtained her bachelor's degree in chemical engineering from the University of Benin in 1988. She subsequently earned both her master's and Doctor of Philosophy degrees in chemical engineering from the University of Lagos in 1991 and 2005, respectively. Professor Babalola's academic career has spanned over 3 decades. Prior to joining the University of Lagos, she worked in various academic capacities at Ladoke Akintola University of Technology, Ogbomoso, the Federal Polytechnic, Bida, and Lagos State University. She joined the services of the University of Lagos in 1999 as an assistant lecturer, and in 2022, she was appointed a full professor, specializing in thermodynamics, energy, and phase behavior, modeling of reservoir and other fluid systems. Among other administrative roles within the university, Professor Babalola has served as acting head of the Department of Chemical and Petroleum Engineering from 2022 to 2023, and as substantive head of department from 2023 to 2024. During her tenure, she successfully midwifed the unbundling of the 22-year-old Petroleum and Gas Engineering program into a full department, thereby strengthening the academic structure of the Faculty of Engineering. Widely respected for her expertise in thermodynamics, reservoir fluid systems, phase behavior modeling, energy systems, and phase stability of fluid systems, Professor Babalola has published extensively in reputable local and international journals. Her scholarly contributions have earned her recognition within and beyond the academic community. One of her most notable research contributions is the co-development of the acclaimed Peng-Robinson-Babalola-Susu equation of state, alongside Emeritus Professor Alfred A. Susu. The innovative model has significantly advanced the accurate prediction of phase behavior and properties of reservoir fluid systems under extreme high pressure and high temperature conditions where conventional models are less effective. Professor Babalola has served as external examiner to several universities across Nigeria, including Lagos State University, Obafemi Awolowo University, and the University of Ilorin. She serves on editorial boards as well as review panels for reputable international journals. She was also a member of the Energy Thematic Group of the Presidential Committee on Vision 2020 and has contributed to several consultancy engagements in the energy sector. She is a registered engineer with the Council for the Regulation of Engineering in Nigeria, COREN, a fellow of the Nigerian Society of Chemical Engineers, and a member of the Association of Professional Women Engineers of Nigeria. Professor Faith Uchenna Babalola, is married to engineer King Olasheni Babalola, and they are blessed with children. Distinguished ladies and gentlemen, it is my honor to invite Professor Faith Uchenna Babalola, the first female academic in the Faculty of Engineering, to deliver an inaugural lecture since the establishment of the faculty in 1964. You're welcome.
The Vice Chancellor, the Deputy Vice Chancellor, Academics and Research, the Deputy Vice Chancellor, Development Services, the Deputy Vice Chancellor, Management Services, the Registrar, the Bursar, the University Librarian, the Provost College of Medicine, the Dean Faculty of Engineering, Deans of other faculties, members of the University Senate, the Head Department of Chemical Engineering, heads of other departments, distinguished academic and professional colleagues, distinguished non-teaching colleagues, dear students and alumni, members of the press, distinguished guests, ladies and gentlemen. It is with great delight and gratitude to God that I stand here today, the 6th day of May 2026, to deliver the 459th inaugural lecture in the history of the University of Lagos. This is the 13th in this academic session, the 51st in the Faculty of Engineering, and the 9th in the Department of Chemical Engineering. All these are not by the doings of humans, but by the appointment and grace of God Almighty. So then, it is not of him that willeth, nor of him that runneth, but of God that sheweth mercy. Romans 9:16. Madam Vice Chancellor, after obtaining my first degree in chemical engineering from the University of Benin, I pursued my God-given vision, which I had nursed since my flair for physics and mathematics in my secondary school days, to go for a PhD in chemical engineering, which brought me to the University of Lagos to begin my master's degree program. I have always desired to be a lecturer since I was a teenager. I did not know then how I would combine some aspects of mathematics and physics that I enjoyed so much, but God, in an amazing way, though unclear to me then, guided me to the field of chemical engineering thermodynamics for my PhD program through the mentorship of my supervisor, Professor Alfred A. Susu, who was churning out PhDs in the department then. Thermo, as we called it, was abstract, complicated, uninteresting to me and most of my classmates. But when Professor Susu taught us advanced chemical engineering thermodynamics at master's level, everything about thermo changed, and I followed that path for a doctoral degree. I had advanced in my PhD research work before I realized that my dream of selected aspects of physics and mathematics were perfectly combined for me in this field. So, an enthusiastic Stanford-trained supervisor and mentor met an enthusiastic student, and a groundbreaking equation of state was developed with 5 publications in reputable foreign journals from a PhD work. I caught the research fire from Professor Susu, and it is still blazing as I mentor younger researchers today. Madam Vice Chancellor, I started school quite early and spent some 3 years in the then uncommon nursery school, so that at 5, I had to begin primary school education. Again, I schooled in northeastern Nigeria, where we had primary 1 to 7, giving me a sound foundation for my academic pursuit with fervor, focusing on my studies almost without any distraction on my part through my first, second, and third degrees. My mother, though a widow, maintained that since God was her husband, as the Bible states in Isaiah 54, he will see to our quality upbringing and all-round development. Our part was to deploy his gifts and be our best for his glory. My flair for mathematics blossomed as I studied both during school session and holiday season. In my senior secondary school years, I realized that mathematics wasn't sufficient to satisfy my interest and curiosity. But fortunately, I found a better platform in additional mathematics to pursue my passion. While at Federal Government College, Maiduguri, my quest was further fueled when I tried unsuccessfully to unravel the intrigues of the Pythagoras theorem, discover the last digit in pi, and do other searches. But I was elated when I successfully derived the equation of a circle in Form 5 before the additional maths teacher, Mr. Nwagu, treated it in class with the hint he gave us while throwing the challenge for us to try. He made additional maths so interesting that he called it mathemagic. Madam Vice Chancellor, my story is a tribute to the grace and love of God, given to me without deserving any bit of it. I started my academic career as one of the founding members of staff in the Department of Chemical Engineering, Lautech, in 1992, with the pioneer head of department, Professor John Edewo, who left Chemical Engineering Department, Unilag, to birth the one at Lautech. I left the same year to Federal Polytechnic, Bida, as lecturer too. I then moved to Lagos State University, Ojo, and came back to Unilag, starting all over as assistant lecturer. I obtained my PhD and rose through the ranks to professorship in 2022. It was remarkable that in every institution where I indicated my interest in teaching chemical engineering thermodynamics, others gladly left it for me to teach. But in Unilag, it was different. I met experienced hands from whom I learned a lot. I taught thermodynamics and some other courses over the years and supervised research projects totaling 219 undergraduates, 25 masters. I've enrolled as supervisor and co-supervisor for 9 PhDs, 1 completed, others still on course. On the administrative front, I headed the department and I attracted funding for laboratory equipment, student scholarship, refurbishing of classrooms, laboratories, and workshops for the 2 programs in the then Department of Chemical and Petroleum Engineering. We also regained NUC accreditation for the Petroleum and Gas Engineering program, which had been lost. I successfully midwifed the unbundling of the Department of Chemical and Petroleum Engineering into 2 departments. This occurred after a protracted tutelage of 22 years for the Petroleum and Gas Engineering program. On the external front, I have been involved in several external services, including external examiner, reviewer for journals, member of Presidential Committee on Vision 2020, and I'm registered with professional bodies. Introduction, Madam Vice Chancellor. The title of my inaugural lecture is Translating Abstract Thermodynamics into Concrete Useful Tangibilities. Thermodynamics as a subject is a big one and a large house, intertwining many subjects and to some extent leaving many either confused or unsure of its scope, span, and depth. These characteristics have led to the subject being perceived by many as abstract. A prominent application of thermodynamics is its ability to develop equations that predict real-life scenarios, thereby avoiding the costly route of numerous experiments for data generation and ultimate engineering project design. For this purpose, data is generated much more cheaply, thereby speeding up the time required in getting products to the marketplace. Thus, thermodynamics should circus the laborious part of initial experimentations, bench-scale investigations, and pilot-scale probes for project implementation. Further, the universal reach of thermodynamics goes beyond the physical sciences and engineering to the social sciences, especially the use of ubiquitous entropy in economics and life sciences. For over 25 years, I have studied and investigated various topics in thermodynamics, especially non-reacting fluid systems, particularly reservoir fluid systems, a complex multi-component, multi-phase mixture of hundreds or even thousands of compounds. Madam Vice Chancellor, in this inaugural lecture, I will cover my past works and contributions in the following areas: equation of state models, fluid phase equilibrium and phase split prediction, spinodal and boiling liquid expanding vapor explosion models, modeling and simulation of reservoir fluid systems, application of rheology of honey as an index of quality, innovative green power generation using organic Rankine cycle. I will conclude by highlighting the tangibility of thermodynamics and its possible applicability to non-mathematical concepts of life interaction. Further, I will deliver my recommendations, direction of my future research, and acknowledgements. First, investigation and findings into the equation of state models. I have carried out major investigations from first principles and fundamental concepts of molecular behavior of fluid substances, using the lens of classical thermodynamics as a robust tool for problem understanding, analysis, mathematical transformation, abstraction, solution, and interpretation for engineering applications. Equation of state were investigated and understood from the most basic concept, beginning with the simplest but practical two-phase equation of state by J.D. van der Waals in 1873, which was for pure systems, to very complex and multi-parameter equations of state, which were developed over the next 130 years. With the monumental work of J.W. Gibbs in 1875, thermodynamic models were extended beyond pure systems. He was the first to show its generality and demonstrated that thermodynamic treatment was possible for a wide variety of scientific applications. With this lecture, Madam Vice Chancellor, I will propose its further extension to real-life interaction beyond chemical and other engineering systems and processes. In our investigation into properties of reservoir fluid systems and their prediction methods, equations of state, EOS, were employed in modeling the behavior of dense multi-component, multi-phase reservoir fluids at various conditions, including conventional and unconventional wells. We modified a few among the existing EOS that have found wide application in the oil and gas industry and recorded very significant improvements in performance for reservoir property prediction. Improvement recorded were in some cases as high as 40%. With the depletion of conventional reservoirs across the globe, research focus then shifted to the search for accurate EOS that will be applicable to phase behavior modeling as well as property prediction for ultra-deep and other unconventional wells. In this quest, we classified various EOS by their applicability to various scenarios with a view to finding promising ones for PVT modeling of ultra-deep, high-pressure, high-temperature reservoirs. 6 equations of state were compared, and you can just take note of number 3, which is Elliott-Suresh, don't know where, equation of state of 1990, and number 6, Penn-Robinson-Babalola-Susu, equation of state of 2005. These were compared for slightly elevated pressure up to 35 megapascal with the then available data. Clearly, from figures 1 to 4, 4 of these equations were good at moderate pressures, while 2 showed high potential for higher pressures beyond this data set. So we can see the 2 coming from top. They are ESD and PRBS. And it shows that they are not applicable for low pressure, but get more accurate as pressure increases. This is the error deviation graph. You can see their error deviation sloping and diving downwards as pressure increases. Even among the 2, PRBS is still lower and closer to 0 than ESD. Okay, and then we'll go to, we concluded then that 2 were most promising candidates, ESD and PRBS, for high pressure, high temperature scenario, up to 69 megapascal, because their percentage absolute deviation decreased with increase in pressure as seen in these figures, Babalola and Oduwole, 2014. For the high pressure, high temperature reservoirs, most widely used EOS model failed to accurately predict reservoir fluid properties and model their phase behavior. The challenges to be addressed in this direction were well catalogued in our work, Babalola et al. 2019, with a clear quantitative demonstration of the various improvements hitherto made through various modification approaches by some researchers for different types of promising EOS up to 120 megapascal. We and some other researchers compared the accuracy of a few EOS modified specifically for high pressure scenario. We applied them to binary system and showed that they still required more improvement to make them applicable to high pressure multi-component systems. An alternative route was then proposed by us for EOS modeling, which could be vigorously pursued by researchers. In this route, rather than apply an EOS to pure and binary systems and then modify it for higher number component systems, we proposed that an EOS already applicable to multi-component systems at low pressure could be modified and adapted for high temperature, high pressure conditions. Since this foreseen promising approach tilted towards the approach earlier employed in the development of PRBS equation of state, we were to some extent confident that our equation of state, being one of the promising ones for high pressure, high temperature scenario, will compete favorably among the few in this category. Madam Vice Chancellor, following this proposed trajectory, we were able to publish a work recently where we included 2 other EOS that were considered by researchers as promising for the HPHT scenario, the cubic plus CPA and the Patoch chain PC-SAPT equations of state. We compared their prediction accuracy over a wide pressure range, Babalola and Olacheson 2024. And their results are shown here. As you can see, this is percentage absolute error deviation. All right? And in that table, thank you, our PRBS has topped the PCSAPT and CPA that the whole world considers as the best. This is the histogram showing it. The Penn-Robinson equation of state, we can see, performs so poorly because the average deviation is very high. So it is not applicable at high pressure. But we included it here because it is our source equation to show the effect of our modification. The celebrated, now tested and proven Penn-Robinson Babalola Susu equation of state is given in this equation. Contribution to knowledge. The Penn-Robinson Babalola Susu equation of state currently ranks among the top promising EOS for high pressure, high temperature reservoir. It is remarkable that this EOS does not require tuning, which is presently done with all others, and is quite involving and expensive. Its mathematical form, being cubic in molar volume, is amenable to software applications. Fluid phase equilibria and phase split prediction models. This EOS, Penn-Robinson Babalola Susu EOS, was extended through a rigorous mathematical procedure to develop a model for phase stability prediction of multi-component, multi-phase fluid systems. The constant parameter A was replaced with a variable parameter A, which resulted in an excellent level of accuracy and intrinsically eliminated the need for expensive and laborious tuning. So, all equations of state treat parameter A as a constant. And in that figure on your left, that is the error that they import into their model. If you treat it, it's actually a variable, but if you do, your model will be too complicated to solve. We found a way to simplify that, and we introduced variable parameter A in our model. And the accuracy is what you have on the right, reduced from 42% to 8%. This is the best we have seen, as far as we are aware. For a reservoir creed, which is associated gas, this was a remarkable discovery and a major contribution to knowledge. Sequel to this, stability limit profile, we employed the PRBS EOS, yes, to develop a stability model for pure systems and determine phase stability limits for N-hexane, cyclohexane, and benzene as representative paraffinic, naphthenic, and aromatic compounds. And that is what we have in this table. Before this, only normal hexane had been determined with a stability limit. We got the same value that they got, and we were able to extend it to other compounds. Sequel to this, stability limit profile for cyclohexane was determined, as shown in figure 11. This profile serves as a remarkable and suitable guide for efficient design because it clearly shows the region of stable single phase below the curve. Not just did we didn't just get the stability limit as a value, we got a model that could generate a profile so that you carry out all your design below this curve to avoid instability zone. We deployed our new stability limit model to determine stability profiles for each constituent of an LNG system and extended it to LNG mixture, as shown in figures 12 and 15. Babalola and Ogunkoya, 2018. This is stability profile for all constituents of LNG, both the liquid and the vapor, and this is stability profile for the mixture. As far as we are aware, this is the first time the stability profile is being developed for a mixture. Still on the quest for a stability prediction model for systems with hundreds of constituents, like the reservoir fluid system, this PRBS EOS was employed in developing such a model that not only determines phase stability, but also predicts phase split and phase separation, when it will occur, at what temperature, and at what pressure. Additionally, it identifies the specific conditions under which phase split will occur. Babalola and Susu, 2018. Stability model for phase split prediction is given. This is our stability model for phase split prediction. We can look at figures 16 to 19. With this model, you can look inside your well, your oil well. Your top left is one of the wells. You can see the vapor and the liquid. And your top right is the stability limit, both for the vapor and for the limit, for the liquid given by the isotherm. Below is very interesting. We got to this well and we saw 3 phases, 1 vapor phase and 2 liquid phases. And we were still able, our model was still able to determine the stability limit of all the 3 wells we considered. And these are their values as given in this table. Contribution to knowledge. Until then, phase stability testing, being such a complex problem, was only determined by a point test at a specific temperature and pressure condition, because it was a precursor to isothermal flash calculation, particularly in the petroleum industry. For the first time, a model was developed to search over a wide range of temperature and pressure conditions and determine if there will be a phase split at all, and when it will occur, and how many phases will be there. Spinodal and boiling liquid expanding vapor explosion models. Just call it BELIEVE model. Madam Vice Chancellor, the binodal curve of a fluid system is the vapor liquid equilibrium curve for a pure liquid. It shows the loci of boiling points over the range of pressure of interest. The spinodal curve, however, for a liquid is the limit of stability when nucleation has been suppressed to the fullest. This means that a system can remain in the liquid state. We can heat water beyond 100 degrees in this hall and it will not vaporize once we can suppress the nucleation sites. However, when suppression becomes impossible with further heating, a spontaneous phase change must occur. This is called explosion, if the phase change is from liquid to vapor. We developed a spinodal vapor explosion model for the first time, Babalola and Ogunkoya, 2018, with a very robust algorithm that served. The curves were generated for all constituents of LNG as pure systems, that of propane, while the search for an adequate, this is for propane, while the search for an adequate one for mixtures is still ongoing. Till then, spinodal points were determined as specific explosion points, and we were able to get this. If your liquid moves towards this extreme curve on the right, you will have explosion. And if your vapor moves to the other curve at the extreme left, you will have implosion, even though that is less common. Figure 21 shows a storage facility and a transportation vessel undergoing BELIEVE at the point of spinodal explosion. This is common with LPG, LNG, other low temperature boiling liquids, and even water. The greatest prevention, apart from basic HSE requirements, is to use a spinodal model like ours and carry out all design and operations below the predetermined spinodal points of temperature and pressure with well-established suppression level for each specific scenario. Madam Vice Chancellor, prediction models are very necessary here because lab prototype experiments that involve actual explosion are not safe, and their micro-level control is still a challenge for now. Design and operations can avoid dangerous instability and explosion and implosion zones defined by accurate models. Our contribution to knowledge by the extension of our stability limit model to incorporate possible suppression, we developed a robust spinodal model which could predict point of insuppressible nucleation leading to explosion and implosion. Numerous accidents that occur in the operation of industrial equipment, storage facilities, and transportation vessels can be easily prevented by using our model for their design. Modeling and simulation of reservoir fluids. We did some work to improve performance of a number of models in the reservoir systems. I just mentioned two here. Our potential fluid theory-based equation was applied to productivity calculation to determine better option between horizontal or vertical wells under given scenarios. Then our multi-tank EMBAR model was deployed to a mature complex field in the Niger Delta, and the solution we profiled saved the company from having to drill another well they had proposed. Application of rheology of honey as an index of quality. We employ the rheology, which is the mechanical flow behavior of fluids, as a tool to determine the quality of honey. Mwalo et al. 2018. With an impressive rheological characterization using a mathematical model developed in our work, termed structural kinetic model, we successfully correlated the degree of adulteration of honey with its molecular weight. A unique profile signature of pure honey was obtained irrespective of its origin. As we can see in this figure, at your extreme left, you see the signature of pure honey occurs between the share rate value of 0 and 0.2 per second. So at a glance, it has to go right up first, which is positive, before going down, which is negative. And so you can assess these honey samples for yourself. On your left, you can see only 2 are pure, all the others are adulterated. Then on the right, we have honey samples from all over the country. Only the pink and the blue are pure honey. All the others are adulterated, imitation, or fake. Look at these samples from across Nigeria. Everything here is adulterated honey. With these rheograms being easily amenable to electronic imaging, a portable device which can determine the composition of any honey sample as well as its percentage purity is, with a few drops, is already in sight. Madam Vice Chancellor, this model breakthrough checkmates the havoc done to consumers through honey adulteration by desperate dealers and provides a novel cost-effective alternative to traditional physical-chemical characterization currently done with very expensive equipment. Sequel to this characterization breakthrough, we proceeded to develop a standard correlation of the rheological properties of honey, first with its physicochemical properties, Anidiobu et al. 2019, and next with its antibacterial activities, Anidiobu et al. 2019b. Working with biochemists, we use bacterial cultures of Staphylococcus aureus and Pseudomonas aeruginosa obtained from the microbiology lab, Ekiti State University Teaching Hospital. The antibacterial activities of honey and our adulterated honeys were successfully correlated using the area of inhibition zone. So the area of inhibition zone, look at the value up there. As you adulterate, it drops drastically or even disappears. But when we got to water, which we now call dilution, we see that dilution with water up to 10% retains the antibacterial potential of honey. For these two considered. And the contribution to knowledge. These contributions to knowledge are major and will save us from many havoc, many things that are done by desperate dealers. Let's go to green power generation using the organic Rankine cycle. The importance of green energy has been on the front burner of the global energy landscape for a while now. This is particularly crucial for Nigeria, where extreme undersupply of energy has translated to high cost of manufactured products and backward trend in industrialization indices. To deploy the ORC for small-scale electricity generation without steam, the main challenge is to find a suitable working fluid with which our tropical overabundant solar energy can be harnessed. Such a fluid, of course, must be environmentally friendly. Madam Vice Chancellor, in our recent work, Babalola and Adelaja 2022, we narrowed down hundreds of working fluids to 6 that are suitable for this purpose. Their overall rankings in thermal and exergy efficiencies are shown in the table before you. So these are the best, and this is how they rank in efficiency. Going further in this work, with our design for optimum turbine inlet temperature, we recently narrowed down selected working fluid and proposed cascading the cycles to optimize power output, specific work output, and system efficiency, as shown in figures 26 and 27. And our findings show that for single fluid, we can use R245CA as the best, both for 2-stage and 3-stage. And then these combinations for a number of fluids. This work is still ongoing, and we are seeking funding and collaboration to address the energy challenge facing our country. Looking forward, my future work in 3 aspects. In the oil and gas, we are currently collaborating with an oil and gas software firm to onboard the now tested and proven Penn Robinson Babalola Susu equation of state onto their software platform for deployment in PVT modeling and phase split prediction. In the renewable energy front, we are at the stage of laboratory test with these few promising working fluids, and this will be followed by pilot stage. Thirdly, I am foraying into global water security. First, nanomaterials for atmospheric water harvesting. We have charted the course to pursue this work and have our first paper in this area already published, Susu et al. 2025. Then development of nanomaterial enhanced membranes for advanced water treatment. We are collaborating across disciplines on this, and we are also seeking funding. Conclusion. Proposal of a generalized thermodynamic model. Madam Vice Chancellor, from the stance of thermodynamics as a subject, all real-life processes or interactions meet the following conditions. They are irreversible, they are non-ideal, they cause increase in the entropy of the universe. They have efficiency below 100 degrees and they 100%, and they occur between equilibrium states. Ironically, even a reversible chemical reaction is indeed an irreversible process in a thermodynamic sense because it cannot return the universe to its initial state without net effect. This implies that every person, place, thing, and useful entity is a system. And so every interaction between systems is accomplishing a real and hence an irreversible process. So in dealing with any process, whether a student studying to gain knowledge, a father training up his children, a marriage relationship, a business plan, or an enterprise, a government project implementation, the repair of a faulty car or equipment, a free and fair electoral process, a building construction, equipment fabrication, computer coding, social interaction, military operations, self-defense, prudent spending, etc. A thermodynamic model can be of use. For each real process, there exists a quasi-static path traversed by equilibrium states of the system which can be approached for optimum benefit for all systems involved as well as the surroundings, which is made up of the rest of the universe. On this quasi-static path, entropy increase of the universe is intrinsically and optimally minimized. This curve, the blue curve on the x-axis, is a reversible process which cannot happen. It is impossible. The red one is the quasi-static path, which is practicable but unattainable. Then the green, yellow, and purple are alternative paths that are practicable. When you have these three paths practicable, you must select the one that is closest to the quasi-static path. The best choice of path for any real-life interaction or process, therefore, is that which is practically determined as the closest to a proposed quasi-static path, so that equilibrium is minimized as much as possible, thereby ensuring minimal entropy increase to achieve maximum possible efficiency with minimal perturbation, disturbance, and disequilibrium. Thermodynamic models can be deployed for real-life situations in order to determine and choose the best possible path which should be closest to the quasi-static path for all systems involved as well as for the surroundings. These panacea models may only be applied qualitatively in the meantime, but can be made quantitative in no distant future. My call to action and recommendation. Funding of research by government for national industrial growth and technological advancements is yet to come to the focus in our country. Hitherto, lip service has been paid to funding of education and research, where many individuals are helping to fund small-scale startups and small research works. But other research work with high cost are left to the researcher with hardly any funding structure. Funding research should not be treated as charity, but as investment. I appeal to the government, organizations, and individuals to invest significantly to fund research work up to commercialization stage so that they can reap their dividends. Appreciation. With a heart of gratitude, I hereby acknowledge those who have worked in various ways to achieve the success marked by today's event. First, and above all else, I want to express my gratitude and thanksgiving to God Almighty for his fatherly love for me. God is outside the universe, and so he is beyond thermodynamics. No mathematics. He cannot be modeled. Acknowledgements. University of Lagos. I want to thank our dear Vice Chancellor, Professor Folashade Ogunshola, FASON, for her leadership of foresight and objectivity, and also her great management team. I am grateful to the Dean of the Faculty of Engineering, Professor Eso Adeosun, and the Head Department of Chemical Engineering, Professor O.A. Olafadeon. I thank the University of Lagos for providing me the conducive environment to thrive. My mentors. I thank my PhD supervisor, mentor, and teacher, Emeritus Professor Alfred Akpoveta Susu. NN1, FAS. He is right here, who has been my mentor till date and showed me that thermodynamics is a tangible subject. Special thanks to Dr. J. Yunwalo, who supervised my master's degree project and gave me the opportunity to train under his mentorship on PhD supervision. I appreciate Professor Sam S. Adefila, an icon in the field of thermodynamics, especially with his deep knowledge of molecular chemistry. He breaks down thermo so you can see and touch it. Thanks to all my teachers who helped to shape me both in mind and character throughout my school years. I appreciate my former students, especially those who have worked on these research outputs showcased here and in my other publications. Department of Chemical Engineering. I want to appreciate the efforts of our pioneer head of department, Professor A.F. Ogunye. He is here. Our former Vice Chancellor, Professor R.A. Bello. I appreciate all our past HODs, my senior colleagues, all academic, technical, and administrative staff, alumni, and students. My large family. I thank God for bringing me into this world through my parents, both late now, Mr. Mwafo and Mrs. Gloria Ibeme. I especially appreciate my mother, who determined after we lost my father very early that all her children would be well educated. That's why my late father's view that higher education was not for girls. She labored with God's help, and now she has 2 female professors. My big thanks to my eldest brother, watching online, I believe, Mr. Ifeanyi Beme, who assumed the fatherly role over us, even before he got married, through many sacrifices. I appreciate you, sir. I appreciate my brothers and my sisters and their spouses. I am thankful to my in-laws. I especially thank God for my mother, very supportive mother-in-law, Mrs. Uchenna Babalola, whom I had already informed about the date of this inaugural lecture, but she passed to glory since October. Special thanks to Reverend Mrs. Mojisola Sonia Olu, Deaconess Deborah Babalola, and all the Babalolas. They are well represented here. I appreciate the Oladipos family, the Makindes family, and the Seses family. My brothers and my sisters, I thank all my past, present, spiritual leaders, brothers, sisters, mentors, mentees, friends from various churches and ministries I have been affiliated with over the years. I thank Reverend Dr. Dino Ajayi, MD Rofe Hospital Agbara, Evangelist Mrs. J.A. Olushoka, President, Believers Mentoring Mission, they are all here. Reverend Mrs. George, Reverend Shaya Awokwetu of Foursquare Gospel Church. I also appreciate Pastor Rebecca Lynn Hardy and Pastor Henry D'Souza of the Online Christian Church. I thank all my friends, and there are too many to list. Thanks to Federal Government College Meduguri Old Students Association, especially class of 83, and Uniben Engineering class of 1988. May God bless you all. My closest family. I appreciate our sons, Toluwani Babalola and Nathaniel Babalola. They are Unilag alumni, and they are IT experts, always assisting me in uncountable ways. Thanks to our baby girl, Boluwatife Babalola. Finally, I thank my husband, also an alumnus of Unilag. I thank my honey, our family president, supervisor, organizer, and daddy, elder, engineer, King Olasheni Babalola. Even sometimes, when I don't want to push further in my career, he would always encourage me to continue while we prayed and trusted God. He urges me on with much encouragement and support to put in my best. I appreciate you, sir. God bless you more and more. Amen. Madam Vice Chancellor, distinguished members of this great audience, thank you for your attention. As I hope that you leave this place with a new mindset that thermodynamics is tangible, and universally applicable. May God bless you. Thank you. Madam Vice Chancellor, I am done. Thank you, ma'am. Wow. Okay.
Please be seated. First of all, I'd like to recognize the presence of Emeritus Professor Alfred A. Susu, mentor of the inaugural lecturer. I can't see him. I also recognize the presence of Professor Sam Adefila and Dr. John Uwalo, also mentors of Professor Babalola. We welcome here the Jagaban of University of Lagos, the pioneer HOD of Chemical Engineering, Professor Ayodele Ogunye. I want to thank Dr. Layo Yeleye, Reverend Dr. Azuka Obolumani, the chaplain of the Chapel of Christ Our Lights, Unilag, Reverend Dr. Diron Ajayi, the MD Rough Hospital, Agbara Estate, Evangel Mrs. Jacinta Olushoga, President Believers Mentoring Mission. Thank you all for coming. Reverend Mrs. Elizabeth George of Foursquare Gospel Church. Thank you for being here. I congratulate Mr. Ifeanyi Ibeme and the entire Ibeme family. You should be truly proud. I also congratulate Mr. Tunde Babalola and the entire Babalola family, the Seses family, the Oladipo family, and the Makinde family. I also congratulate the children, greatest Akokites, Toluani Babalola and Nathaniel Babalola, and the future Akokites, Miss Bolua Tife Babalola, whom we're expecting. Last but not the least, I congratulate the encourager, the president of the family, the king of his castle, the organizer, supervisor, daddy, and honey, unadulterated, Professor Elder Engineer King Olasheni Babalola. Congratulations. I recognize the presence of former principal officers. I believe I can only see one, Professor Bolanle Obbo, former Deputy Vice Chancellor, Academics and Research. The Deputy Vice Chancellor, Development Services, Professor Afolabi Leshi. The Deputy Vice Chancellor, Management Services, Professor Muyiwa Falaye. The Deputy Vice Chancellor, Academics and Research, Professor Matthew Ilori. The Registrar and Secretary to Council, Mrs. Abosede Wycliffe. The Bursar, Mrs. Oluwafumilola Adekunle. The University Librarian, ably represented by Professor Adetun Adekonye. The Provost College of Medicine, Professor Ademola Oremosu. The Dean Faculty of Engineering, ably represented by Professor Folorunsho Ogunwolu. Distinguished ladies and gentlemen of the press, I am sure you will agree with me as we listen to the 459th inaugural lecture of our university, translating abstract thermodynamics into concrete, useful tangibilities, delivered by Professor Faith Uchenna Babalola. That this lecture has successfully demystified the often abstract discipline of thermodynamics, presenting it as a practical, tangible, and indispensable scientific tool with transformative applications across engineering, industrial processes, and everyday life. Our inaugural lecturer demonstrated how thermodynamics serves as the foundation for solving complex scientific and engineering problems, particularly in the oil and gas sector, where the Peng-Robinson-Babalola-Susu equation of state has achieved high precision in modeling pressure, volume, temperature behavior, and predicting properties of high pressure, high temperature, multi-component reservoir fluid systems. Extending thermodynamic principles into safety engineering, Professor Babalola developed an innovative predictive model for the prevention of liquid explosions and gas implosions in metastable systems, thereby offering safer alternatives to hazardous physical experimentation and improving industrial safety in process operations, transportation, and storage. In a compelling demonstration of interdisciplinary innovation, she also applied her thermodynamic knowledge to honey, presenting a thermodynamic-based adulterant detection model designed to be incorporated into portable electronic devices to facilitate affordable and efficient product quality assurance. Addressing the nation's energy challenges, Professor Babalola was able to identify suitable working fluids from thousands of possibilities for the deployment of organic Rankine cycle systems, thereby advancing the use of abundant solar thermal resources for medium-scale power generation and contributing meaningfully to Nigeria's renewable energy aspirations. Today's inaugural lecture stands as a testament to the power of scientific abstraction translated into practical innovation, bridging theory and application, academia and industry, and ultimately contributing to technological development and national economic growth. Professor Babalola has not only advanced the frontiers of thermodynamic science, but has also inspired us to rethink its relevance as a universal tool for innovation, optimization, and problem solving in our modern world, such that common devices, machines, and software packages can be built from these abstract equations and hopefully will appear in the marketplace sooner than later. We expect that Professor Babalola will utilize the AI Unipod, the NIT Hub, or the Fab Labs to produce prototypes of these simple devices based on her findings. Professor Faith Uchenna Babalola, congratulations on giving an excellent and interesting inaugural lecture with immense contribution on improving our society and the world at large. We congratulate you and your faculty. I thank you all for coming and wish you safe return to your various destinations. I hereby declare this assembly closed.